Hi everyone, my name is Joey Carlson. I'm with the Department of Electrical and Computer Engineering at UC San Diego, and today I will be presenting our work on energy efficient tri-hybrid precoding with dynamic metasurface antennas. And this was previously presented at the 2023 Asilomar Conference. So first I want to discuss a little bit about the background of this problem and why we're looking at tri-hybrid precoding for dynamic metasurface antennas. So in a millimeter wave and terahertz communications, as well as thinking about massive MIMO, future wireless communication systems are really looking to increase the number of antenna elements in our array. And so we show here an analog precoding architecture with a large number of antenna elements in our array that are densely packed together to just create a very large aperture with many elements. Now, while this may have some benefits in terms of performance, such as tight beam steering, with having many antenna elements, that could also scaling up the number of antenna elements could also scale the power consumption and hardware footprint for our system. So for example, for an analog precoding architecture with phase shifters connected to each antenna element, scaling up the number of antenna elements is also going to scale up the number of phase shifters and power amplifiers for our system. For a digital precoding architecture, this would involve scaling up the number of RF chains as well. And so we ideally want to have a solution where we can scale up the number of antenna elements without scaling up the power consumption or hardware footprint of our system. And so one of the proposed solutions to this problem is to use reconfigurable apertures or reconfigurable antennas. So on the left there we show sort of our baseline, the phased subarray, where each antenna has a connected phase shifter. And so while this enables good beamforming performance, it is what's typically done. There are many components involved, such as phase shifters, power amplifiers, and a power divider, connected to all the different antennas, which can all contribute to the power consumption for the system, which especially increases as we increase the number of antenna elements. Now, instead of a phase subarray, we can also think about a reconfigurable antenna array, where instead of beamforming with phase shifters, we can beamform with we can control the antennas themselves. And the reconfigurable antennas have some reconfigurable components integrated into the antenna, and we can use an external controller to control the antenna and then enable beamforming. And so while this lowers the power consumption and hardware footprint, there are still many components involved here, such as the power amplifiers and the power divider for this antenna array. Now, the third approach that we're looking at here for a reconfigurable aperture, or for an array, is the dynamic metasurface antenna, which is a type of slotted waveguide antenna array, a reconfigurable slotted waveguide antenna array. And so this has the benefit over reconfigurable apertures in the second picture there, that the waveguide architecture allows for a single feed into the entire antenna array. So we require a single power amplifier and no power divider, and then all the different elements atop of the waveguide structure, which are the antenna elements, can enable beamforming via the external controller. So the dynamic metasurface antenna can really lower the power consumption, use minimal components while still enabling beamforming for our antenna array. And so now we can look a little bit into the prior work on the DMA signal processing literature. So a large majority of the prior work on dynamic metasurface antenna signal processing is limited to the digital baseband, looking at a digital baseband precoder and a DMA precoder. And so here we show a pretty typical implementation in some of these prior references listed below, which includes a digital baseband precoder, and then the DMA precoder, where we have some external DMA control to control each of the DMA elements. This forms sort of a DMA hybrid precoding. Much of the prior work considers this model, and they also consider very ideal DMA models for how to model the different antenna weights on them. And so while these papers are useful and result in a lot of interesting results for how to maximize spectral or energy efficiency, we want to look a little bit further beyond using the digital baseband precoder and the DMA precoder to another layer of precoding, and also incorporate more practical DMA models to more accurately model the DMA antenna weights. So then our proposed next step to extend some of this work is to look at a tri-hybrid architecture. So rather than only having digital and DMA precoding, we want to also add in analog signal processing. So we have the digital signal processing component, an analog signal processing component with something like phase shifters, and then we have the antenna precoding, which for this is the dynamic metasurface antenna. And so looking at this from both the transmit and receive side, we can imagine a full tri-hybrid architecture where we can determine the different trade-offs within our system for spectral and energy efficiency and power consumption to optimize our system with all of these three different precoding techniques. So now we'll talk a little bit about what a dynamic metasurface antenna is. So as I alluded to a little bit, the dynamic metasurface antenna is a type of reconfigurable slotted waveguide antenna. And so we see on the left the excitation or the feed to this is a waveguide excitation, and then power is radiated out through little slots in the waveguide as the different antenna elements. Now the important thing to note about this, the DMA, is that it has a very specific geometry that allows for a resonant response. And within that DMA geometry, there are tunable components, which in this case we're considering varactor diodes, which is a tunable capacitor that actually alters the resonant frequency response of the DMA, which is how we can enable beamforming with the dynamic metasurface antenna. And so varactor diodes and other reconfigurable components often consume minimal power and have a minimal hardware footprint, so they're low cost and do not take up a lot of space. So we can enable these low power beamforming with dynamic metasurface antennas through these reconfigurable components. So now in terms of precoding with dynamic metasurface antennas, individual DMA elements are normally modeled as a magnetic dipole. And we can use this magnetic dipole approximation to determine the polarizability for a dynamic metasurface antenna as listed in that equation in the upper right there. And so there are some different attributes to this DMA polarizability, such as the coupling or damping factor there, that are determined by that DMA geometry, and those different design parameters affect the polarizability. But the important thing to note here is that this magnetic dipole model allows us to model our effective antenna weights for the dynamic metasurface antenna based on this magnetic polarizability. So we can actually use this equation for the alpha of m there as our effective antenna weights in our DMA precoder for the DMA. And it's important to note that the varactor diode there, as we see on the left, is what we are using to change the resonant frequency, which is how we tune the dynamic metasurface antenna elements. Now, while DMAs have these great advantages in terms of power consumption and hardware footprint, naturally there are some downsides to dynamic metasurface antennas in terms of beamforming and performance compared to a phased array. So first, because of this waveguide fed architecture for dynamic metasurface antennas, the waveguide fields affect the beamforming in the sense that they introduce an inherent phase advance into the system, which is determined by the propagation constant for the waveguide. And so when we're doing beamforming with the DMA, we actually have to take into account the physical properties of the waveguide to ensure that we can steer a beam in a desired direction. Moreover, due to the reconfigurable component for the DMA, we actually have a limited weight distribution compared to something like a phased array for beamforming. And so we show that on the right. We have our ideal phase shifter, which is unit amplitude, 360-degree phase range. And we have our DMA Lorentzian constrained distribution, which only has access to the lower half of the imaginary plane and has a coupled amplitude phase constraint. And so this distribution is what we use for DMA precoding, but naturally it restricts it. There is some beamforming degradation when compared with a phase shifter, possibly in terms of gain and maybe steering direction or steering accuracy. Now, to do beamforming with a dynamic metasurface antenna, one very simple approach is to map your desired weight, so your phase shifter weight, your phased array solution, onto that Lorentzian constrained distribution. And so here we show something called Euclidean mapping, where you simply take the desired weight and then minimize the Euclidean distance between your phase shifter, your unit amplitude solution, to the DMA weight or the Lorentzian constrained distribution. And so this minimizing the Euclidean distance allows for us to create a DMA, or to tune the resonant frequencies for the DMA and create our effective DMA precoder to steer a beam in a desired direction. And it's a very simple, low complexity solution for beam steering with DMAs. Now, we can enable joint analog and digital and DMA precoding via this method by tuning the DMA precoder with that Euclidean mapping technique, and then subsequently tuning our analog, or calculating our analog precoding vector and then our digital baseband precoding vector with this process. And so, with the addition of the DMA precoding vector, we can do everything in MIMO OFDM the exact same, but with the addition of this FDMA, this precoding matrix, I guess, thrown into the mix. And we also need to make sure that we account for the frequency selectivity of the DMA, since that resonant response was highly frequency selective, as we saw in one of the previous slides. And so now jointly configuring all of these three different precoding vectors can allow us to do some interesting optimization in terms of the energy efficiency, power consumption, and spectral efficiency. We could do some analysis to determine how many RF chains we want, how many phase shifters we want, and how each of these different components impacts the resulting energy and spectral efficiency to really optimize our system and say, to maximize energy efficiency, we may want these components, but to maximize spectral efficiency, maybe we want to differ this a little bit to maintain a certain power consumption. So we want to do a joint, we want to jointly configure the DMA precoder and the analog and digital precoder to maximize the spectral efficiency and determine these different trade-offs. Now, taking a look at some of our prior work, this is listed in the reference 1 there, we were able to develop a DFT codebook with the DMA and get some HFSS results for these. So rather than using idealized DMA models, we're actually obtaining electromagnetic simulation results for the beam patterns to use in simulations, to use in simulation results for spectral and energy efficiency. And then also comparing this with a phased array, we actually found that DMAs can enable much more energy efficient communications compared to the traditional, active and phased arrays. And for the active phased array with active phase shifters by nearly twice, by nearly a 2x difference for the DMA. So we found with some of these simulation results for energy efficiency that DMAs can really lower the power consumption and improve the energy efficiency of the dynamic of the whole system, which is why we want to look at that one step further. And while this considered only analog precoding, enable that tri-hybrid precoding to see how we can further improve the energy efficiency. So now we'll sort of conclude and have a few concluding remarks here. So the dynamic metasurface antenna, we can use some non-ideal models and work with the dynamic metasurface antenna polarizability to determine some of the antenna weights and use electromagnetic simulation results to obtain beam patterns. And then we can use these as our DMA precoding weights and obtain those beam patterns in electromagnetic simulation results for the DMA precoder. And then we can maximize energy efficiency by calculating a joint dynamic metasurface antenna, analog, and digital precoder to maximize energy efficiency and look at the performance in terms of spectral efficiency and power consumption as well. Thank you so much for listening to my talk, and for more information, please refer to the full paper. Thank you.